Hi everyone! In the previous video, we have discussed the statement of the division algorithm. Now let us proceed to its proof, which consists of two parts. The first is the existence, the second is the uniqueness. In this video, we will deal with the existence, leaving the uniqueness to the next video. The idea for this part is actually fairly natural and simple. To better understand it, recall the story of ribbon and ruler explained in the beginning of the previous section. There, we have used 6 to divide 20. It turns out that the quotient is 3 and the remainder is 2. How did we actually find these numbers? Well, we simply keep taking off copies of 6 from 20. In other words, we considered natural numbers of the form 20 minus 6x, with x being 3, 2, 1, and so on. We did not stop as early as 2, because when we take off another 6 from 8, the remaining number is still non-negative. We did not go as far as 4 neither, because when x is equal to 4, the remaining part is already negative. Now, it is clear why we stop at 3. This is because 2 is the minimum among all the natural numbers of the form 20 minus 6x. Now, to generalize this idea, simply let A play the role of the ribbon and B play the role of the ruler. This suggests that we should study the set S, which consists of all natural numbers of the form A minus bx, with x being an integer. Notice that x can be positive, negative, or 0, but we must guarantee A minus bx is non-negative. Now, before we go any further, there is a tiny yet important detail we should justify. That is, we should show S is non-empty. And how do we show that? We simply pick some specific x and compute what is the value of A minus bx. Here, let us take x to be negative absolute value of A. Direct computation shows A minus b times negative absolute value of A is equal to A plus b times absolute value of A. Now recall that b is a positive natural number, which is at least 1. Hence, this term is greater than or equal to A plus absolute value of A, which is always non-negative. And now, this number is of the form A minus an integer multiple of B. Moreover, it is indeed a natural number. Hence, we conclude that A minus B times negative absolute value of A is an element in S. This shows that S is non-empty. Now, since S is a non-empty subset of the naturals, it must permit a minimum. Let us call R the minimum of this set. Since R is a minimum of S, it is a priori an element in S. Thus, by the definition of S, R is equal to A minus BQ for some integer Q. Notice that this is very close to what we want to show, as we can rewrite this equality as A is equal to B times Q plus R, which is precisely the equality in the statement of the theorem. But be careful, we have not finished yet. It remains to show that R thus achieved is indeed in the desired range. In other words, we need to show that R is greater than or equal to 0 and is strictly less than B. It is straightforward to show that R is non-negative. Since R is an element in S and every element in S is non-negative, so is R. To show that R is less than B, we use the proof by contradiction. Assume otherwise that R is greater than or equal to B. Then let us consider the integer R minus B. Based on our previous assumption, we know that R minus B must be non-negative. Moreover, recall that R is equal to A minus BQ. Replacing R in the term R minus B by A minus BQ, we see that R minus B is equal to A minus BQ minus B. And after combining all terms with B together, this gives A minus B times Q plus 1. Now, R minus B is of the form A minus an integer multiple of B. Moreover, it is non-negative as well. Again, based on the definition of S, we conclude that R minus B is in S. Now, R minus B is an element in S. R is the minimum in S. Since every element dominates the minimum, this implies R is less than or equal to R minus B, which in turn implies that B is non-positive, contradicting the fact that B is a positive natural number. From there, we conclude that R being greater than or equal to B is impossible. As a result, R is less than B. This finishes the proof for the existence. In the next video, we will prove the uniqueness.